Let's continue our discussion. In the last video, we have discussed about angular acceleration, angular acceleration, which was denoted by alpha, and it is nothing but time derivative of angular velocity. So, as in case of linear motion, the acceleration was caused due to force. In the same way, there should be a physical quantity here in case of this rotational motion, or in case of this angular acceleration, there should be a cause for this angular acceleration. Means a kind of rotational analog for force. So this quantity is torque and also known as moment of force, and you can call it also couple, but generally we call it torque, and it is actually moment of force. So let us discuss this torque for a single particle, and then we will continue to multi-particle system. So let's say we have this coordinate axis. This is x coordinate, x axis. This is y axis. This is z axis, or you can call it g axis, whatever you like to call. So let's say there is a particle here at point P, and its position from origin is r. This is position vector, and this is origin. And let's say there is a force being applied on this particle. This is force, and the angle between the force and this position vector is theta. So this torque is defined as tau vector. This is Greek symbol tau. We use it for torque, and this will be r cross f. This is defined as this moment of force or torque. Now we know r cross f can be written as it is cross product. We can write it rf sine theta, and there should be a unit vector. Let us write it n cap with subscript tau. Okay, so first of all, we can find out this direction easily because we have to use that right hand rule r cross f, and then we are placing the fingers along the direction of r and then curling it towards f will give us the direction of this torque. Means the thumb will give us the direction of this torque. So we have done this thing already. In this particular case, if I am saying that position vector r and this force, these two are in yz plane, then the direction of torque will be, or this n cap will be along the positive axis. So this n cap tau will be here, nothing but I cap. So let's continue our discussion. So this is its direction part. Now coming to its magnitude part here. So this is r and f sine theta, and this is n cap. This f sine theta, what is the f sine theta here? Let me try another color. So if we check this is angle theta with this base. So we can create here a triangle, and I am doing that thing here. Let's say this is force, and this is the direction of r, position vector, and this is angle theta. So this vector will be its perpendicular component, and this vector will be its horizontal component. I hope this is visible, clearly visible. Okay, so I can write it here also. So this is f perpendicular. So I can write it here also. This is f perpendicular. This is f perpendicular vector, and this is f horizontal here with respect to this position vector. So r and f sine theta will be equals to this much. F sine theta, and let's say there must be some vector sign here, so I'm taking its magnitude only, or magnitude of this horizontal component will be f cos theta. We have done these all things earlier, so this will be f perpendicular in tau. Okay, we can arrive at the same situation, uh, trying different approach actually. How can we do that? Okay, let me continue it here also. So torque equals to r cross f, and we know f can be resolved into its components, f perpendicular and another component f horizontal, And we know R cross F here perpendicular plus R cross F horizontal and R cross F perpendicular. These two have the angle between these two is 90 degree. You can see it easily here. Here you can see it. Okay, let me try this color. So this angle is 90 degree with R vector and this angle is 90 degree here. Here. Okay. So this will be sustaining here, but this will be zero because the angle between this R and this horizontal component of this force will be 0 degree. So RF sine theta is not going to sustain here. So we will have ultimately this one RF perpendicular and then sine 90 degree here and then unit vector. Ultimately it will be RF perpendicular unit vector. So we have arrived at the same result here. Now let's take a practical scenario and then we can analyze little bit more about this torque or this moment of force. So let us take a scenario here. Okay, let's say we have a spanner, bolt spanner, bolt, bolt spanner here. Okay, so let's say this is bolt spanner here. This is bolt spanner, which we use to open a bolt. And this is, okay, this is bolt spanner. And let's say we are trying to open this bolt here inside. So you can imagine this situation. So here we have a bolt and we are trying to open this bolt using this bolt spanner. And let's say this point will be here. This point will be through where the axis of rotation passes. So if this is z axis, isn't there different color? Okay. And this is, let's say, y axis and this is z axis. Sorry, x axis now. So, okay, this is not good. This is z axis. Okay, so we are trying to open this bolt, and now we know that we need to apply force on its arm here. We have torque equals to Rf sine theta. Okay, and for direction we can get it easily. So let's try to analyze what will be the effect of various R, F, and theta on this torque. So this is right-handed bolt. So if it is right-handed, it will come out if we rotate it anti-clockwise. So in this particular case, we are trying to rotate this bolt spanner and then we are trying to open this bolt. Now, with the help of this, we can analyze the situation. What will be happening? What if someone tries to apply a force on this line? L means this line passing through this origin or passing through a point where axis of rotation line. This will be the axis of rotation here. This will be the axis of rotation. So what if we are applying a force here? We are applying force here. So F is something, but R is 0. And at the end, we are not going to give any torque or we can't rotate this bolt applying force here. What if we are applying here? You can think in general. If you have experienced such a scene, you can say which force is going to create more impact near this origin or away from this. So you can say easily that if we apply force at greater distance, the torque will be more, or we can give it more rotational effect, or we can open this bolt easily. So with increasing R, this is what happening here. We are increasing the point of application, or we are increasing the magnitude of position vector. So with increasing this R, we can increase this torque. So if we are increasing R, we can increase this torque. Now, what about force? We know at some point, let's say at this point, if we are applying different forces, force 1 greater than force 2 greater than force 3. So in which case it will be opened easily. Means in which case the rotational effect will be more. We can say that if force is more, this torque will be more. So we have F. If we are increasing F, this rotational effect will increase. Now what about the angle, this theta? So this is position vector. Let me make diagram again, or we can just erase some part and we can continue. So what about this theta, changing theta? So let's say this is point origin, and from here at some distance we are applying the force at an angle of 0 degree, means the force is along this. Will it be open or not? You can answer it easily that it is not going to open. So if we have this theta between R and F is 0, the torque will be 0. What if we are applying force just opposite to the direction of this position vector? So in this case also theta will be 180 degree, but the torque will be again 0. So when this torque will be maximum, you can say it from here between 0 to 180, the maximum value of this sine theta will be at theta equals to 90 degree, and you can practically realize this thing. When you apply the force exactly perpendicular to this position vector, you can generate the greater effect, or entire case greatest effect. So if this is 90 degree, this torque will be T max. So if you are changing force here to different directions, as you are moving from 0 to 90 degree, the torque will be maximum. Again, if this force is changing its direction and it is coming to 180 degree, from here it will start decreasing and then it will come to 0 again. Now, we had linear momentum there in case of translational motion. So there should be an analogous thing here also, and that thing we call angular momentum. So what is angular momentum? Angular momentum, you can also call it moment of momentum, or let me write it, angular momentum, or you can call it moment of momentum. And if I'm saying momentum simply, it means linear momentum. I'm saying here linear momentum. Okay, in the same way, if we are denoting the angular momentum by this letter L, small l, the moment of momentum will be R cross P. As the moment of force was R cross F, the moment of momentum will be R cross P. You can say its SI unit and its dimension. Do it by yourself. What will be dimensional formula for L? Now, this will be R P sine theta and n cap, let's say, with subscript L. You can again proceed in the same way. It may be R sine theta, that is perpendicular distance between momentum and the origin or point of reference, times magnitude of this linear momentum and this one. Or you can write it R, as it is written already, P sine theta, which is perpendicular component. Perpendicular means it is perpendicular to this R vector, position vector R. So you can write it R perpendicular, as we have done it already in case of torque. The same way we are following here. So you can write angular momentum equals to this thing, or you can write angular momentum equals to this thing or this thing, whatever you want, or whatever is of use while solving problems. Okay, then. Now, as we know, the time derivative of momentum, means linear momentum, was giving us force. So if this angular momentum is analogous to linear momentum in case of rotational motion, the torque should be related to the same way as the linear momentum is related to the force. That is, time derivative of this angular momentum should be related to torque. Okay, we can do it. Let us do. What will be dl by dt? So dl, we can write it r cross p dt. Now we can write here dr by dt cross p plus r cross dp by dt. If you don't know this thing, you have to understand a little bit of calculus here. So this is what we have to do. First, we have to take first function derivative here. If two functions are multiplied and then multiplied with second function, and then we have to multiply it with first function and derivative of this second function. So this is what I have done here only. Okay. So this will be dr by dt will be velocity vector and cross momentum and then plus r cross. This is course linear in case of linear motion. So we have arrived at the same scenario. This is moment of force or torque, and this is going to be zero. Why I'm saying this is going to be zero? Because v cross mv, or you can write m v cross v, and we know this thing is zero, v cross v. So ultimately, time derivative of this thing is torque. So we have completed these all things for single particle system. We can continue this to next class in case of system of particles, and then we will do some problems or examples related to it. So that's all for this video.